Before starting the next lesson, try this warm-up question. What is the difference between speed and velocity? You may have heard these terms before, maybe you think they mean the same thing, or maybe you've taken a physics course and you know the difference. Pause the video and take a minute to think about it, or do some research. Then come back and we'll take it up. So hopefully you found this out. Speed and velocity both refer to how fast an object is traveling. However, velocity includes direction of travel. So if I say that I'm driving 100 kilometers per hour in my car, that's speed. If I say I'm traveling 100 kilometers per hour north, that's velocity. So velocity includes direction. And this idea is good to keep in the back of your mind as we go through this unit. Velocity is an example of a vector, and so this unit is all about vectors. And so this lesson is the basics of vectors. So by the end of this lesson, hopefully you'll be able to explain the difference between vectors and scalars. So I'll talk about what that is. And then you should be able to determine equivalent vectors given a diagram. So I'll go through some terminology, some examples, and hopefully by the end you'll be able to do these things. Now in the warm-up I talked about the difference between speed and velocity. Well, these are actually examples of scalar and vector. So a scalar is a quantity that has a magnitude. A vector is a quantity that has magnitude and direction. So as an example, scalar would be the speed, vector equivalent would be velocity. So in speed, the magnitude is the number, right? It's the 100 kilometers per hour. That's the magnitude. And then the direction would be, well, I'm traveling north, or I'm traveling north 30 degrees east, something like that. Some other examples you might be familiar with are distance and displacement. So I can say I walked 30 kilometers. That's a distance. Or I can say I walked 30 kilometers east. That's displacement. So the overall thing you got to remember is the difference between scalar and vector. Scalar is magnitude, a number, a numerical value, whereas a vector includes the magnitude with a direction. Okay, let's move on. Now, when we're dealing with vectors, we're going to be drawing a lot of pictures. Okay, so here's an example of what you might see. It looks like a line, but be careful, take some note on this. It starts at a point, and we have an arrow tip on the end. So this line isn't just a line, it's indicating a vector. There's magnitude, the size of the line, but it also indicates direction. And you might also have an angle to show you the more precise direction that the vector is pointing. Now, just when I'm talking about how the vector is drawn, the part that is here is called the tail, and the part that has the arrow is called the head. Now, if we're representing a vector algebraically, we need a symbol for it. And so it's kind of like a variable. You have a letter. I'll just use U. Usually that's what people use for a vector. But it has a little arrow on top. So you might see it with a full arrow or a half arrowhead, kind of like a harpoon. Both of those just mean you have the name of the vector, and then the arrow indicates that that's what it is. It's a vector, not just some other variable. Okay, so if you have a letter with an arrow on top, that's going to represent a variable. Another way you might see it is, let's say the vector is labeled from A to B, then you could call it vector AB, and it would be written like that. Now, sometimes in a question, you might be told that the angle between two vectors is 30 degrees, for example. Well, you have to be careful because you have to make sure that your vectors are connected at the tails. so tail to tail, and then the angle between them would be there. You do not want to draw your vectors tail to head, because then your angle in here, it's not going to be the right thing. Okay, so don't draw it like that. Draw it like that. Now I want to talk about scalar multiplication. So here's 3 different vectors that I've drawn. Vector u, vector v, and vector w. I'll just call them u, v, and w. Okay, so I can see vector u. U is this vector. It's 4 units long. V is 8 units long. W is also 4 units long. However, notice the direction. U and V point to the right. W points to the left. Okay, so U is not the same as W. Now, scalar multiplication, what do I mean by that? Well, remember, a scalar value is magnitude only. Okay, so I can multiply my vectors by a scalar amount. So I can multiply my vectors by a number, and that number can create an equivalent vector to something else. So here's an example. V equals 2u. So if I took u and I added another one, so if I had 2 u's, it would equal v. 4 plus 4 is 8, and they're going the same direction. So 4 to the right plus 4 to the right equals 8 to the right. So vector v is the same as 2 vector u's. Now if we look the other way around, u is half the length of v. Now they're going in the same direction, so u is exactly half of v. So that's what I wrote here. Now, algebraically, I could just rearrange this, divide both sides by 2, I get u equals v over 2. That's the same thing. Now look at this. U is equal to negative w. So why is it negative? They're the same size. They're both 4 units. However, notice the direction. U points to the right, W points to the left. They're going in opposite directions. So that's why we have opposite signs when we represent this algebraically. So although the magnitudes are the same for U and V, the direction is different. So we have to show that with a negative value. And I can do a similar thing. W is half the length of V, but it's in the opposite direction. So I can indicate that with negative half of V. Okay, so the scalar multiplier can indicate a change in magnitude and a change in direction. So keep that in mind as we work with vectors in this unit. The next thing I want to talk about is something called a zero vector. So algebraically, we can write that as a 0 with a vector symbol. Geometrically, it's just a dot. Okay, no arrow, because there's no magnitude. The magnitude is 0. The direction can be any direction. So we'd have no arrow on the dot. Okay, so zero vector just means there's no magnitude, there's no direction, and that can come in handy later. Okay, some more terminology here. Unit vector. Unit refers to 1. Okay, so what do I mean? Well, let's say, for example, you have a vector u pointing in a certain direction. We have an angle there. And vector u has a certain magnitude. Now, if I refer to a vector with the same direction, but just with a unit of, or a magnitude of 1, then I can call it the unit vector, and I label it with the same symbol with a different hat. Okay, so it has an upward pointing arrow on top. That refers to the unit vector. We're not really going to use that too much right now, but that idea will come into play a little bit later in the unit. And the last little bit of notation terminology that I want to talk about is, what if you have a vector and you don't really need to worry too much about its direction? What if you're just referring to the magnitude of a vector? So let's say we have vector u, and I want to say, well, the magnitude of that vector is 6 meters. Okay, so U represents displacement, and I want to say the displacement was 6 meters, but I don't really need to indicate the direction. So we use these absolute value bars. Okay, so let's say, for example, the magnitude of my vector U is 6 meters. Notice I didn't put a direction here. So when you see the absolute value bars around a vector symbol, that just means we're talking about the magnitude only, the size only, and not the direction. Okay, done with notation and terminology. Let's do some examples. Example 1, list some equivalent vectors in the diagram. Okay, so this diagram, I've got different points, A, B, C, D, and E. They're all connected with lines, and each line can represent a vector. Okay, so I can have equivalent vectors. So when I say equivalent vectors, what I'm talking about is not just the same magnitude, but also the same direction. Okay, so let's go through this. So let's look at vector AB. I've shown it here from A to B. So I've got my arrow pointing this way. What is another vector that is the same magnitude, so the same size, and also the same direction? Well, the only other one that we have is down here from D to C. Those are equivalent vectors because they point in the same direction and they have the same magnitude. They are the same size. Take a minute and try this on your own. So pause the video, see if you can come up with some equivalent vectors, write them down, and then when you're ready, check back in and see if we got some of the same ones. Okay, I've written down some. I haven't written all of the equivalent vectors that you can come up with, so some that you wrote might not be on my list here. So I've got AD equals BC, same direction, same magnitude. AE equals EC, same direction, same magnitude. Now some examples down here, you might not have really thought about these ones. AD is equal to AE plus ED. So AE plus ED, we start and finish in the same spot. If you start and finish in the same spot, then your overall vector is the same size as AD. Okay? Same with AB plus BC plus CD. Well, from A to B plus from B to C plus from C to D. That's the same as starting from A and ending in D, A to D. Okay, so that's what this means. So you can add vectors together and get an overall result that is the same. And as I said, you might have written down some vectors that are equivalent, but they just might not appear on my list because I didn't write down all of them. But I think you get an idea of what we're going for here. And here's my second and final example for this lesson. List some equivalent vectors in this diagram. Okay, so here it's all on a line. I've got different points, A, B, C, D, E, and I've indicated the lengths of each line segment on here. Okay, so why don't you take a minute, pause the video, and see if you can come up with some equivalent vectors, keeping in mind that you can add vectors together, and you can use those scalar multipliers as well. So pause the video now and try it. Okay, so here are some that you might have come up with. AC, well, that's 5 units to the right. CD is also 5 units to the right. AC is 5 units to the right, and that's the same as AB plus BC, because we're going 3 units to the right plus 2 units to the right. So overall, it's the same, 5 units to the right. Now BD, from B to D, we're going a total of 7 units to the right. DE is also 7 units to the right. AB is 3 units to the right. I can say that's equal to CD minus BC. CD is 5 units to the right. BC is 2 units to the right. So if I take 5 units to the right and I subtract 2 units to the right, then overall I'm only going 3 units to the right, which is the same as AB. Now another way I can think about that is CD is 5 units to the right, CB is 2 units to the left. So if I take CD and I add CB, it's the same thing. I'm going 5 units to the right, and I'm adding 2 units to the left. So overall, I'm going 3 units to the right, which is the same as A to B. So, okay, so BC and CB, those are vectors that are equal in magnitude, just opposite in direction. And so that's why the sign is different in front of those. So just keep that in mind. Now something else I want to show you. Let's say, for example, AC. Okay, AC is 5 units to the right. Now let's compare that to DE. It's 7 units to the right. Okay, so if I compare AC to DE, well, what fraction of DE is AC? Well, if I took DE and I divide it by 7, I'd get the unit vector. And if I multiply it by 5, well, then I'd get a magnitude of 5 going in the same direction as AC. Okay, so another way I can think of it is AC is 5/7 of DE. Okay, so if I divided DE into 7 equal pieces and then used 5 of them, that would be 5/7. That's 5 units to the right, same as AC. Okay, so I just wanted to show you, you can have that scalar multiplier in front of a vector in order to make an equivalent vector. So why don't you pause the video and see if you can make another one like that, and then check back in to see how you did. Now here's one example. I have BC, so 2 units to the right, is, if I relate that to CE, well, CE, well, that's 12 units to the right. So if BC is only 2 units compared to the 12 units of CE, well, it's 2/12, or 1/6 of CE. Okay, now you probably had something different than I did there. As long as the length of the vector over here multiplied by the scalar value in front is the same as the vector you wrote over here, then you're good. And just make sure that the letters are written in such a way that they're going in the same direction. So that's the lesson. So you've got a lot of new terminology and notation to keep track of. I'd like you to work on the practice problems now, just so you get used to all this stuff before we get too complicated. Okay, and if you have any questions, please reach out and I will do my best to help.